coordinate plane.
As you may remember, these ordered pairs can be plotted on a graph, where the horizontal axis of the graph represents values for x, and the vertical axis of the graph represents values for f of x. Using our function f of x equals 2x plus 1, we can plug in values of our domain, specifically -2, -1, 0, 1, 2, and 3, to get the range or y values. We can then plot these ordered pairs or points of a function on our graph. See here.
Of course, you've seen graphs before, but you're probably used to seeing the f of x value written as a y value. Don't let this little ruse confuse you. They're the same thing. So if it's easier for you to think of f of x as y, then go right ahead. After all, earlier we used y before we replaced it with f of x. The important thing to remember is that x is the domain, or independent variable, and is graphed on the horizontal axis. And f of x, or y, is the range, or dependent variable, and is graphed on the vertical axis.
New Mexico.
It's Idaho. What happened to you, old sidekick?
I got run over by a goat. Listen, before I die, I must tell you something.
What is it?
F of x can also be written as y.
I knew that.
In algebraic functions, the domain doesn't have to be made up of whole numbers. It can also include decimal or fractional values. So, instead of considering only 2 and 3, we would also allow 2.87, 2 2/3, 2.222 repeating, and all the other possible numbers between 2 and 3. These whole numbers, fractions, finite, and infinite decimals are all referred to as real numbers.
Palays? Real numbers? Okay, come on, how duh? Like there are numbers that aren't real?
Well, actually, Veronica, there are numbers that aren't real. For historical reasons, they're referred to as imaginary numbers, although in strictly philosophical terms, they are, of course, real enough.
Yeah, okay, first, it's not Veronica anymore, my name is V. Second, you smell, and third, get some new glasses.
Just think of real numbers as the numbers that get used in everyday life. Whole numbers, fractions, and decimals, including repeating decimals like 0.3333, etc. This is what you get if you try to convert the fraction 1/3 to an exact decimal. There is another kind that goes on forever without repeating any pattern. It is infinite, like 3.14159265359, etc. The number you recognize as pi.
Pi?
Surprisingly, there are actually more of these infinite non-repeating decimals than there are of any other kind of real number. They show up often as a result of solving equations in algebra. That means that many algebra problems do not have answers that can be given exactly using fractions or normal, finite decimals. Still, finite or infinite, all decimals are real numbers.
A typical domain for a function might consist of all of the real numbers between 2 and 3, or all of the real numbers between -4 and 4, or between any other pair of values. There are an infinite number of real numbers in any such set, and they crowd infinitely close together, so graphing the function results in an infinite number of connected points. All these points plotted together will form a line or curve, the graph of the function.
We'll get back to real numbers and graphs later. For now, let's look at a practical example of a function.
Section C, a practical example.
Simon Wright, a bullwhip maker who owns Ye Olde Bullwhip Shop, can make 2 bullwhips in one day. Starting this morning, he has 1 bullwhip that he made yesterday. Business hasn't been very good lately, so assuming he does not sell any whips, how many whips will Simon have by the end of the day? In 3 days from now, in a week from now. A simple function can be used to solve this problem. In this case, the function will be a relation between the number of days that have passed and the number of whips that Simon has. We know that this morning, after 0 days, Simon had 1 whip. By the end of today, after 1 day, Simon will have the 1 whip he started with plus the 2 whips he made today, which totals 3 whips. Tomorrow night, after 2 days, he will have the 1 whip from yesterday plus 2 whips from today plus the 2 more whips that he'll make tomorrow. So he'll have a total of 5 whips.
Following this same pattern, after 27 days, the number of whips will be 1 plus 2 plus 2 plus 2, and so on for 27 twos. That is, there will be 1 plus 2 times 27, which equals 55 whips. If we use the variable x to stand for the number of days, the pattern can be like this. After x days, there will be 1 plus 2x whips. That expresses the number of whips as a function of x, because as soon as the value of x is known, we can immediately compute the number of whips. Using the standard form, we write f of x equals 1 plus 2x, where x is the number of days that have passed, and f of x is the number of whips that Simon has. If 3 days have passed, then x equals 3, and the number of whips is f of 3 equals 1 plus 2 times 3, which equals 7. So in 3 days, Simon will have 7 whips. If a year has passed, then x equals 365, and f of 365 equals 1 plus 2 times 365, or 731. So in a year, Simon will have 731 whips, assuming he doesn't sell any, which, based upon current whip trends, seems pretty likely. As we said, all functions can be graphed. By plotting all of the x and y values of Simon's function, we can see that it looks like this.
Hey,
Oregon!
it's Idaho. Give me a whip.
There you go.
Thanks. Let's try this thing out. You actually sell these things?
Now, sometimes when you do practical word problems like this, the domain is restricted by the meaning of the variable. In this case, it doesn't make logical sense for x to have a negative value because x in this equation represents time, and time doesn't run backwards. So in this case, x is greater than or equal to 0. This is just another instance of real life interfering with algebra.
We know that a function is defined as a relation where each value of the domain is paired with one and only one value of the range. So, there is only one value for f of x that is paired with any given value of x. We can make sure that a graph is a function by using the vertical line test.
To start the vertical line test, you set a vertical line on the graph and move it along the horizontal axis, or x-axis. We'll use the function of Simon's whip inventory to demonstrate. As long as the line touches no more than one point of the graph of the equation, then the graph is a function. But if it ever touches the graph of the equation at more than one point at any place on the graph, then the graph is not a function.
Oh, hello, Mr. Barnes.
Wrong parody, old man. Listen, we need your help.
Can you tell us about this function?
Oh, we'll use an ancient Chinese secret. If you move a vertical line along the x-axis, you can tell if this is a function. If it only touches the graph at one point at any time, then it's a function. What you have there is not a function.
Well, what is it?
Oh my God, that's a takeout menu for pearls. I'm hungry.
Oh, it's the lost function of the covenant. It'll take you to winter crop.
Winter crop, winter crop, rah, rah, rah. Yeah?
Let's go.
Section D, Inverse Functions.
We don't want to leave this introduction to functions without mentioning the concept of the inverse function. Thinking visually, inverting a graph means to reverse the coordinates of each point on the graph.
For example, if 2, 5 is one of the points in the original graph, then 5, 2 will be a point of the inverted graph. If 3, 7 is another point in the original graph, then 7, 3 will be another point in the inverted graph. Here are some examples of graphs and their inverses. You can see that the original graphs and the inverted graphs appear to be mirror images, with the mirror placed along the diagonal line y equals x. The reason for this will become clear upon reflection. Changing around the coordinates from 2, 5 to 5, 2 flips a point across the diagonal line.
Inverse functions can be really useful in solving problems. It's not critical to understand exactly why or how right now. We'll see more of this later. But one quick example might give you an idea of what's going on.
Here are the graphs of two functions. F of x equals 2x plus 4, and g of x equals 0.5x minus 2. Notice that these two graphs are mirror images of each other. That is, each graph is the inverse of the other. Now check this out. Plug x equals 3 into f and compute the answer. Then plug that answer into g. So, f of 3 equals 2 times 3 plus 4 equals 10. Plugging 10 into g, we get g of 10 equals 0.5 times 10 minus 2, which equals 3. You get back to your starting point, 3. Let's try another one. If you plug x equals 2 into f, you get 8. Then, plugging 8 into g, you end up with 2 again. The same thing happens for any starting point. The functions f and g counteract each other. If you apply f to a number, you can reverse that operation by applying g to the result. This is the reason that f and g are inverses of each other. Just as addition is considered to be the inverse of subtraction and division is the inverse of multiplication, so g is the inverse of f.
Coiled plastic snake toys. Why has it always got to be coiled plastic snake toys?
And it's the neon pink ones, boss. They're the really dangerous kind. You better go first.
I've been bitten. Give me an antidote.
Oh, you mean algebraically speaking, you want the inverse function of f, which is g? Oh, I guess not. He probably means this.
Inverse functions work like this. If f of x tells you the number of bullwhips there are after a certain number of days, which is x, then g of x will tell you the number of days it will take for Simon to have x number of bullwhips. So earlier we used a function to compute the number of bullwhips for a given number of days. The inverse function will solve the opposite problem. It will compute the number of days for a given number of bullwhips.
Graphs aside, there is also a technique that works directly on the equation of a function to turn it into its inverse.
Quiz 2.